part 2 of lesson 38. We left off talking about the inverse of an exponential function, and we said we need to give it a name, because calling it x equals b to the y just isn't good enough. We need to get y by itself. The name that we came up with is a logarithm. That's what a logarithm is. A logarithmic function is the inverse of an exponential function. And just to make sure we're all clear about what that means, we've seen this before in here. Every time we talk about functions, we want to be able to talk about inputs and outputs. In an exponential function, the exponent is the input. Like the example we graphed in the last section, the input we're putting in is the exponent, and we're going to raise 2 to whatever that input is, and the output, the y value that we get, is the product, the result of all that multiplication. A logarithmic function does the opposite. The exponent is the output, which means what we would do is take the output, the product from the exponential function, put it into the logarithm, and we use this symbol for logarithms, log. We read that as log. We'll talk more about how we read that in a second. And the output is the original exponent that you started with. And this matches what we saw last week when we talked about inverses of functions. That the idea of an inverse function is some new machine, some new rule that we can take the output of a rule we're already familiar with, like an exponential, plug it into this new machine, and have the original input come out, meaning we're going back to where we started from. That's the idea of an inverse. So the way we write this is on your screen. The way we read it, we would say that as y equals log base b of x. And just like with the exponentials, there are a little bit of restrictions on b. This base that we're talking about, it has to be greater than 0. We don't have negative bases, and it cannot be 1. That should sound familiar because those are the same restrictions we had from exponentials. And here's what the graph looks like. Just like exponential functions had a name that we use, exponential growth, and the exponential growth that we saw last lesson and also on the first part of today's lesson was the exponential growth that just gets faster and faster and faster. Logarithmic growth, now it is growth, it does keep going up forever, but it slows down over time. That's the point of logarithmic growth. That's where you see it show up in the real world. Anytime you've got growth that slows down over time. And just some examples of things that do grow logarithmically that you'll see in your word problems. Volume and the way human ears, I guess other animal ears too, experience sound is logarithmic. Earthquakes, the way we measure earthquakes anyway, are logarithmic. If you've heard of the Richter scale, the Richter scale would be the y value up here, and the x value would be just, we'll call it the size of the earthquake, or the strength of the earthquake would be a better word. An earthquake has to be very, 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 very strong to make the Richter scale go up, because the growth slows down over time. There are other examples that we will come across as we go through our youth.